Okay, today in the second last video on our further integration topic in Extension 2, we're going to have a look at the fun world of recurrence relationships. Now, we've seen recurrence relationships previously in further mathematical induction. Now we're going to really hone in on a specific use of recurrence relationships, and that's through integrating. So recurrence relationships can express an integral, and the integral needs to express some sort of function as a power of n. And the function of another integral includes the same function to a different power of n. So, for example, we can prove that the integral from 0 to 1 of x to the power of n is equal to 1 minus x squared dx, which is equal to 1 minus n on n plus 2, integral 0 to 1 of n minus 2 root 1 minus x squared. What you'll more commonly see, though, is what we call a reduction formula, which is kind of reducing the integral into something that's a bit easier to work with. So this integral here is the same as that integral there, except the power of n is now n minus 2. So we could say it's this kind of coefficient of the integral times by the original integral, but n minus 2. Now, we use letters such as I in recurrence relationships, or you might see a U or an A. We can use anything we want to, and we leave the integral written in complete form sometimes. Now, we often use recurrence relationships to evaluate integrals with very high powers by breaking them down into functions of a lower power of an integral that we can integrate. Now, there's many different methods here. We're going to look at 3 methods here, and it's important that we memorize what method to use. If you don't, you're just going to be taking a lot of time to do a question. So, as a rule of thumb, we look at the coefficient of the lower powered integral on the right-hand side, which is in minus 1 or in minus 2 or something like that. Here's 3 examples. Here, the coefficient of this lower power integral, so here's the higher power integral and here's the lower power integral, is minus n. The coefficient of the lower power integral here is n minus 2 and n minus 1, and the coefficient of the lower powered integral here is minus 1. Examples A and B are when we have something to do with n involved in the coefficient. So if the coefficient involves n, such as example A and example B, then we use integration by parts. The number of the coefficient, the numerator, of the coefficient, gives us an important shortcut. It's what we use as the power for u, and we're going to get to that in a second. Now, if we don't have an n in the power, like this one here, we don't use integration by parts, and we're going to use some sort of other method. So, example number 1 is we're going to use a recurrence relationship. I might actually come to this example last. I want to do that example last. I might do these quick ones here first. So, some examples of what I was just talking about in terms of what method to use. So if I've got the in is equal to the integral from 1 to e squared of ln of x to the power of n dx, and that integral we're saying is equal to the reduction formula e squared 2n minus n times by in minus 1. So here the coefficient of the lower integral involves n, so we're using integrating by parts, and the numerator of this n is n over 1, so we're going to use u is going to equal x to the power of n. So that tells us what the power is going to be. This question here, the lower integral here, coefficient is n minus 2 n minus 1, so we're using integration by parts because it involves n, and the numerator is n minus 2, so we're going to let u equal sec n minus 2. Last one here, well, we've got the lower power integral is n minus 1, and its coefficient is n, so we're using integration by parts, or IBP, and the coefficient is n, so n is going to be our power, but notice we can't get n from this, it has to be 2n. So it's going to be 2n is our power. The next example doesn't involve n in the coefficient here. And because of that, we're going to do something else, and we're actually going to plus this over to here and prove that these two integrals added together is equal to this. And the last method we'll come to soon. You've got two n's, and that actually is implying to us that we're going to use integration by parts twice. So example number 2, so we'll get back to example number 1 at the end of this video. So example number 2, if in is equal to x to the n e to the x, prove that in is equal to the reduction formula x to the n e to the x minus n I n minus 1. So this is an example of an integration by parts question, and that's because n is here on the lower power integral and the numerator is n, so we're going to let u, I might do this over here, let u equal x to the n. That means u dash is n x to the n minus 1. And we're going to have to let v equal to the second thing, e to the x, which means v is also equal to e to the x. So we're going to use our tick method to integrate by parts. So this is equal to x to the n e to the x minus the integral of n times by e to the x, x to the n minus 1. Okay, dx. Now, this is where recurrence relationships are not tricky. They're not that difficult because we don't have to do these complex integrals, because this bit simply here is simply this integral, but the n is now n minus 1. So this is just x to the n e to the x minus n I to the n minus 1, or I sub n minus 1, because the n has just been replaced with n minus 1 and we're done. And we don't need to put a plus c because this is still an integral. We haven't actually integrated really anything. Yeah, so we're done. So example number 2 in this is we're looking at using recurrence relationships to integrate cos to the power of nx dx, and we've got to prove that in is equal to cos n minus 1x sine x on n plus n minus 1 on n I to in minus 2. We don't, and it looks scary, I'll admit that it looks scary, but we don't care about this at the moment. We're realizing that this is an integration by parts question, and that's because this is n minus 2 here, and the power is the numerator is n minus 1. So we're integrating by parts, but we are letting u equal to cos n minus 1x. Now we can't just randomly pull out cos n minus 1x from nowhere, so we need to say that this is cos n minus 1x times cos x dx. We can't just randomly pull this out of nowhere. We have to get it from the question, because to integrate by parts we have to choose two functions from the actual question. So that's it there. So u is equal to cos n minus 1 of x. Now we're going to use the chain rule to differentiate this. Bring down the power, n minus 1, times by the new power, times by the differentiation of the brackets, which is minus sine of x. And then we're going to subtract 1 from the power, so cos n minus 2x. So that's equal to minus n minus 1 sine of x cos n minus 2 of x. Okay, that means v dash has to equal cos of x, because that's the other function left in the question, which means v is sine of x, because the integral of cos of x is sine of x. So all we have to do now is integrate by parts using our tick method. So this is equal to sine of x cos of n minus 1x. It's looking pretty good because that is that there. Take away. Now if we take away and we multiply that by that minus is going to die. So let's just straight up write plus. I might pull the n minus 1 out straight away. Integral. This is going to be sine of x times sine of x is sine squared of x cos n minus 2x. Okay. again, we're still not quite in the form. We can't just do what we did in the previous example and go, okay, that is I n minus 2. We can't do that because there's an annoying sine x here. So what we might do is go, okay, well, let's just leave that for a second. This is going to be plus n minus 1, the integral. This is going to be 1 minus sine squared of x, 1 minus cos squared of x times cos n minus 2. So we know that sine squared of x is 1 minus cos squared of x. So this is going to be 1 minus cos squared of x, and that's come from here, times by cos n minus 2 of x dx. So this is plus n minus 1 integral cos n minus 2 x dx minus, what's that, cos squared of x? Oh, no, it's not. So cos squared of x times by cos n minus 2 is, well, 2 plus n minus 2 is n, so it's cos n of x, and I might just put the dx all the way at the end like that and put some nice brackets around there. Right. So if we have a go at expanding this again, this is actually I n minus 2, and that's I n. So this is going to be n minus 1 outside of I n minus 2 minus I n. Because that's the original integral, but instead of n, we've now got n minus 2, and that there is just the original integral right there. We've got equals sine of x cos n minus 1 of x, that's still there. And that is equal to I of n. Okay, so we might have a go at rearranging this. We might expand some things here. So this is equal to sine of x cos n minus 1x plus, what have we got? N minus 1 I n minus 2 minus n minus 1 I of n. I might plus the I of n over to the other side. Do we want to do that, or do you want to expand? Minus n I of n. I'm thinking what we might do, let's just plus it over to the other side at the moment. So we're going to have n minus 1 I of n plus I of n equals sine of x cos n minus 1 of x plus n minus 1 I n minus 2. Now if we expand this through here, we're going to have ni of n minus I of n plus I of n. So the I of n's will die, and it's going to be ni of n equals sine of x cos n minus 1x plus n minus 1 I n minus 2. And we just divide by n, and we're done. So n is equal to sine of x cos of n minus 1 of x on n plus n minus 1 on n I of n minus 2. That one was actually really easy. Okay, let's have a look at the next one. How many examples do I have? 1, 2, 3 more. Okay, so we're looking at I of n is equal to the integral of tan n of x dx, and we are required to prove that it's I of n, that integral is equal to 1 on n minus 1 tan of n minus 1x minus I n minus 2. Okay. The thing that's different about this question is it's no longer an integration by parts question, and that's because the coefficient of your lower power integral is no longer an n, it's a minus 1. So the strategy with that is we're going to figure out what I of n, we're going to plus I of n minus 2. So what's I of n plus I of n minus 2? Well, of course, that's going to be equal to the integral of tan n of x, that's just I of n, plus the integral of tan of n minus 2x. Now we can combine that into one integral because it's both with respect to x, so we're allowed to do that. So just go dx there. Let's take out a common factor of 10n minus 2. We're allowed to do that. Multiplied by, that's going to be tan squared of x plus 1. Bing bang boom, that's equal to sec squared of x. So this is equal to the integral of tan, there should be an x there, Tom, tan n minus 2x sec squared of x dx. Okay. And that's quite an easy integral to do because the integral of tan of x, sorry, the differentiation of tan of x is sec squared of x. So well, let's go let u equal tan of x, which means du is equal to sec squared x dx. So we can replace that with du. So this is u to the n minus 2 du, which is u plus 1, we get n minus 1 on n minus 1, because n minus 2 plus 1 is n minus 1. We're not going to plus c because we're doing a recurrence relationship. We don't care about that really. So this is equal to tan of n minus 1 x on n minus 1. And we have just found what in plus in minus 2 is, which is not quite what we wanted to find. However, so this is, so this is 1 on n minus 1 tan n minus 1 x, which is actually, I think that's what we wanted to prove. So I think we have done, sorry, ignore what I just said. So yeah, we've proven that in plus in minus 2 is equal to that. So therefore in is equal to 1 on n minus 1 tan n minus 1 x minus in minus 2. Okay. Example number 4 asks us to use a recurrence relationship that we actually proved in example 1 of this video, which is the integral of x to the n e to the x dx is equal to in x to the n e to the x minus nin minus 1. And we're going to use that recurrence relationship to evaluate the integral of x cubed e to the x. One of the main uses of recurrence relationships that we're going to use and realize from this example is that recurrence relationships helps us evaluate higher order or higher power integrals from a base case that's easy. And we do that by proving the integral in general and then build up those cases up to the integral we want from the most basic case, which is usually I0. So let's find I0. I0 in this instance is going to equal the integral of x to the 0 e to the x. Now x to the 0 is 1, so this is e to the x dx, which of course is e to the x plus c. Generally it's easiest to start at I0 unless it's impractical or impossible to substitute 0. If you're maybe dividing by n or something, then you would start at 1. But most cases you'll start at 1, so most cases you'll start at 0, rarely you'll start at 1, and even rarer you'll start at 2. So we've found I0. What we're going to do is find I1, I2, and I3. So I1 is equal to e to the x times by x to the 1 minus ni0. And we're going to substitute in our I0 at the end. Now I2 is going to equal x squared, and I actually should put an n. The n in this case is 1, so 1 times I0. X squared e to the x minus 2 minus 1 is 1. Now we know that I1 is x e to the x minus I0. So this is x squared e to the x minus 2 lots of x e to the x minus I0. And if we expand that, that's x squared e to the x minus 2x e to the x plus 2 lots of I0. Okay, now we want to get to I3, which is our goal. I3 is going to equal x cubed e to the x minus 3 lots of n minus 1, which is I2. Now I2, we've just figured out, is x squared e to the x minus 2x e to the x plus 2 lots of I0. So if we expand that, we're going to get x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 2 lots, so in 2 times 3 is 6, so minus 6 lots of I0. Now I0 was e to the x plus c, so this is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x, and our plus c remains there. We don't need to say plus 6c because it's just some constant c. So therefore, the integral, and I might state that here, the integral of x cubed e to the x dx is equal to that. That was a lot of fun. I enjoyed that question. Okay, the last part of integrating by parts is what happens if the recurrence relationship is not given. So in most and all of the recent HSC questions, recurrence relationships have been given, but they don't necessarily have to. Now, the advantage of giving the recurrence relationship is we can use the tricks that we've seen throughout this lesson to know whether we're using integration by parts and therefore the correct value of the power. But what if it's not given? If it's not given, generally we're going to focus on the v dash part of my integrating by parts. So I'm going to rewrite this integral as the integral from 0 to 1 of x to the n, x squared plus 1 to the power of minus 2 dx. Now, I might rewrite just over here, let's find the differentiation of that there. Well, if I were to differentiate that, I would bring down the power, minus 2. I would times it by the differentiation of the brackets, 2x, and I would subtract 1 from the power, x squared plus 1 to the minus 3. Okay. So the problem with this question is that we don't have the differentiation outside the brackets. And to use the reverse chain rule, we need the differentiation outside the brackets. So we want 2x to be outside of the brackets. So let's put it outside the brackets. 2x, let's put it here. Now to do that, this would have to be x to the n minus 1. And we would need to put a half here. Now that means the same thing. So we're going to use that and we're going to integrate by parts this expression here, because this is in the form of the reverse chain rule, so it's very, very, very easy to integrate. So this v dash is going to be 2x, x squared minus 1 to the minus 2, which of course, nice and easy, that means v is just going to equal minus x squared plus 1, not minus 1, to the minus 1, using the reverse chain rule. Easy. So the other thing we have to let u is going to be a half x to the n minus 1, which means u dash is going to equal a half n minus 1 x n minus 2. Let's integrate by parts. How fun. So this is going to equal, times those together, we get minus a half. We're a definite integrating here. So it's going to be that times that, which is x to the n minus 1 over x squared plus 1. That's because that's a negative power there, from 0 to 1. And we're minusing the integral, but since there's a minus here, it's going to be plus the integral from 0 to 1 of x to the n minus 2, x squared plus 1. I feel like this is going to be a very long question. X squared plus 1 over x squared plus 1 squared, I think. Let's have a look. X squared, wait, no, sorry, let me just backtrack here. X to the n minus 2 times by, I might bring out the n minus 1, so that's a half n minus 1 on 2 over x, yeah, that's better, over x squared plus 1. So all I've done is multiply those two things there. Okay. Not the most ideal thing to integrate, and that's because we don't have the differentiation of the bottom on the top, so it's not going to be an ln. The only thing I can think of doing here is we might want to multiply the top and bottom by x squared plus 1. Now if you evaluate this here, you're going to have 1 over 1 plus 1, which is 1 over 2, minus 0. So this is going to be minus 1/4 plus the integral, we've got n minus 1 on 2, integral from 0 to 1. Let's times the top and bottom by x squared plus 1, because that's going to make it much easier, because then we can expand the top, and if we expand the top, we're going to get x to the n, and we're going to have a minus x to the n minus 2, and it's going to be a bit easier to integrate that. So that's going to be x to the n minus 2, x squared plus 1 over x squared plus 1 squared dx. And that's going to equal minus 1/4 plus n minus 1 on 2, the integral from 0 to 1 of, if we expand that, we're going to get x to the n minus 2 times x squared, which is x to the n, plus x to the n minus 2 over x squared plus 1 squared. Now you might think, okay, how did I know that I wanted x squared plus 1 squared? Where did that come from? Where did I pull this multiplication out from? Well, when we're stuck with bits like that, and I should have explained this in the previous step, the reason we're doing that is because the denominator of the original question was x squared plus 1 squared. And in this step, we did not have that in the denominator, so we couldn't apply our recurrence relationships. Remember, recurrence relationships doesn't involve extremely complex integrals. We're trying to rearrange our integral to become the base case of the integral that we're trying to prove or find a relationship for. So since the thing we were trying to find a relationship for had a squared on the bottom, we need to get a squared on the bottom by multiplying the bottom by itself. But if we multiply the bottom by something, we've got to do the same to the top. So we integrate that. That's going to be 1/4 plus n minus 1 on 2, integral from 0 to 1. We can split this into two integrals, x to the n on x squared plus 1 squared, plus x to the n minus 2 on x squared plus 1 squared. Now the reason I've done that is because these are two lots of in with different powers of n. So this is equal to 1/4 minus 1/4 plus n minus 1 on 2 outside of in plus in minus 2. So this is equal to, this is equal to in is equal to minus 1/4 plus n minus 1 on 2 times in plus n minus 1 on 2 times in minus 2. Now we want to make in the subject, so we're going to plus this over to here, and that will get us 3 minus n on 2 equals n minus 1 on 2 what's going on there, n minus 1 on 2 n minus 2 minus 1/4. So if we just divide all of that over, the 2's are going to cancel a lot, so that's going to die there with that one, and this is going to die and become a half. And then we can divide the 3 minus n over. So this is in equals n minus 1 on 3 minus n, n minus 2 minus 1 over 2, 3 minus n. And that's our answer. Thank you for watching.